This is the fourth video in our series on Lie algebras, and today we're going to play the game of classifying Lie algebras with small dimension. And in particular, we're going to classify all Lie algebras of dimension 1, 2, and 3. And that's a little bit of a lie because when we work with Lie algebras of dimension 3, we will mostly restrict ourselves to Lie algebras over complex numbers. In other words, the base field is complex numbers. But for dimension 1 and 2, it'll be true for arbitrary fields. Okay, so let's look at Lie algebras of dimension 1 first. And this is actually pretty fast. That's because there's only one isomorphism class. So if we've got a Lie algebra of dimension 1, then L is spanned by a single vector. I'll call that vector V. But then if we take x and y inside of L, that means that x is equal to a times v and y is equal to b times v. But then if we look at the bracket of x and y, that's the same thing as the bracket of AV with BV, which by bilinearity is the same thing as AB times the bracket of V with itself. But then by the alternating property of the bracket of V with itself is 0. So here we get A times B times 0. In other words, we have 0. But this is for essentially arbitrary x and y inside of L, given that we have a one-dimensional vector space here. So that means that this Lie algebra is abelian. But if it's abelian, that means, well, the bracket is trivial. And so an isomorphism of abelian Lie algebras is the same thing as having an isomorphism of vector spaces. And an isomorphism of vector spaces is wholly dependent on the dimension, none of the other structure. And since with an abelian Lie algebra, there's really no other structure, that means that all abelian Lie algebras of a certain dimension are isomorphic. In particular, since all one-dimensional Lie algebras are abelian, then they're all isomorphic to each other. So that means with a dimension 1, we've got a single isomorphism class. Okay, so let's move on to dimension 2. Okay, so now moving on to two-dimensional Lie algebras. Well, of course, we have abelian two-dimensional Lie algebras. We can have abelian any-dimensional Lie algebras. But those are all isomorphic by our previous discussion. So that means we should probably move on to talking about non-abelian Lie algebras with two dimensions. So let's explore those right here. Okay, so let's suppose that L has the following basis, and that basis is made up of vectors v and w, and this thing is non-abelian. Okay, great. But now that means that if x and y are inside of L, we can write x and y as a linear combination of v and w. So let's do that. We can write x as AV plus BW, and we can write y as CV plus DW. And well, where are A, B, C, and D from? Well, they're from the field. So here we have A, B, C, D are inside of the field. So this is all just using the vector space structure of L. Okay, so now what I'd like to do is calculate the bracket of x and y and see if we can get anything out of that. Well, note that that's going to be the bracket of AV plus BW with CV plus DW. But now by the linearity here, we can expand this out. So note that we'll have A times C times V with V. So let's write that down. So A times C and then the bracket of V with V plus A times D and then the bracket of V with W. And then B times C, the bracket of W with V. So let's get that written down. And then finally, we have B times D and then the bracket of W with itself. But now, of course, we know that some of these are equal to 0 by the alternating property of the bracket. So in particular, this is equal to 0 and this is equal to 0. Furthermore, Again, by the alternating property of the bracket, we know that the bracket of W with V is the same thing as negative the bracket of V with W. So that means here we can write this as AD minus BC, and then the bracket of V with W. But now let's recall we had a certain subalgebra called the derived subalgebra, which was spanned by all vectors of this form. But let's note that since this arbitrary vector, which is in the derived subalgebra, is in this case a scalar multiple of the bracket of V with W, we know that L prime is simply a one-dimensional Lie algebra spanned by this bracket of V with W. Okay, and now at this point we're gonna forget X and Y. And what I mean by forget X and Y, we're just gonna forget that we did this calculation up here. This was just kind of some motivating calculation. And now at this point, we're gonna set X equal to the bracket of V with W. We know that's non-zero, and we know it's non-zero because we've decided this is a non-abelian Lie algebra. And since V and W span the whole vector space, well, you know, that means that this has to be non-zero. If it were zero, we would have an abelian Lie algebra. Okay, so we're setting X equal to that bracket, and then we're going to extend to a basis X, Y of L. So anytime you have a basis for a subspace, which we do here, X is a basis for L prime, we can extend a basis for a subspace to a basis to the whole space. That's like a fact from linear algebra. Okay, great. But now let's note the following. So we have X, Y. Well, X, Y is inside of L prime, but L prime is spanned by X, so we know this is of the form A times X. And furthermore, we know that A is non-zero, and we know that A is non-zero again because this thing is abelian. So that means that we could scale Y. So I'll just say that we choose Y or rescale Y after the fact so that XY bracket or bracket XY is equal to X. So now that we've done that, let's step back and notice that what we've done is we've started with an arbitrary non-abelian two-dimensional Lie algebra, and we found a basis for it. That basis is made up of vectors X and Y, satisfying the bracket relation that bracket XY is equal to X. But notice that all of the other brackets between basis vectors are zero, just because all that's remaining is X with X and Y with Y. I guess there's Y with X, but you can cover that with just the skew symmetric property of the bracket. So that means that there is, up to isomorphism, a single two-dimensional non-abelian Lie algebra. So let's write that over here. So for non-abelian Lie algebras, we can find a basis, and I'll use the notation over here, X, Y, where bracket XY is equal to X. And that's possible for every non-abelian Lie algebra of dimension 2. Okay, so now that we've covered these two cases, let's move on to dimension 3. So now we're ready to look at three-dimensional Lie algebras, and we're going to break this down into a couple of cases. And those cases are going to be based on the dimension of the derived subalgebra. So we talked about the derived subalgebra in the two-dimensional case, but let's recall what it is. So the derived subalgebra L prime is equal to the span of all vectors that are outputs of the bracket, essentially. So in other words, it's the span of bracket XY as XY ranges through all elements from the Lie algebra L. So I think in a previous video we calculated the derived subalgebra for a couple of Lie algebras, so we got our hands dirty with some examples. Okay, so the first case, which is totally trivial, is what happens if the dimension of L prime is equal to 0. But that means that X bracket Y here is simply equal to 0 for all x, y in L. That's the only way to get a zero-dimensional L prime. But if the bracket is always 0, then we have an abelian Lie algebra, and we already talked about what happens when we have an abelian Lie algebra. Those are isomorphic depending on their dimension. So let's move on to this next case where the derived subalgebra is one-dimensional. And we're going to break that into a couple of cases. So, like I said, we're looking at the case when the dimension of the derived subalgebra is 1, and the first case will be when L prime is contained in ZL. So in other words, L prime is a subset or a subspace of the center. Okay, so now let's get going. So since L is non-abelian, well, that means that we can find two elements of L whose bracket is non-zero. So let's do that. So let's find x and y in L such that bracket xy is non-zero. So that's possible because it's non-abelian. And now let's define z to be equal to that bracket. So z is defined to be equal to the bracket of x and y. But now z is inside of L prime. Well, it's a non-zero vector inside of L prime just based on the definitions of everything. But L prime is one-dimensional. That means z is in fact a basis for L prime. So let's write that down. So we have L prime is equal to the span of this vector z. And in fact, z is a basis. And then let's also notice that L prime is contained in the center. If we bracket anything from L with z, we get 0. So we could do that set-wise as follows. So we'll just write bracket L with z is equal to, well, the trivial vector space, the 0 vector space. Okay, now we're going to move on to the following claim, which will essentially finish this whole thing off. And that is that the set containing x, y, and z is a basis for L. And so what are x, y, and z? Well, x and y were any two vectors from the Lie algebra whose bracket is non-zero, and z was their bracket. That's really all there is to it. Okay, so let's see how this might go. We're just going to show that it's linearly independent. So in other words, this set is linearly independent. And then, well, we get the spanning property for free. That's because L is three-dimensional. And then if this is linearly independent, we have a three-dimensional subspace of a three-dimensional vector space, meaning that it's the whole vector space. So let's recall if we have the correct number of vectors, then linear independence and spanning are equivalent. And that's what we're using here. So now let's suppose that we have a linear dependence relation and show that all of the weights of the vectors has to be 0. That's like the standard outline for a linear independence proof. So in other words, let's suppose we have A, B, and C, which are elements of the field, such that AX plus BY plus CZ is equal to 0. Okay, nice. And now the name of the game here is simply to bracket this with X, bracket this with Y, and see what we get out of that. Okay, so let's do that. So let's notice that 0 is the same thing as 0 bracketed with y. I think that's pretty clear. But then that's the same thing as ax plus by plus cz bracketed with y, where I've just replaced 0 with that expansion. But now we can use bilinearity to write this as a xy plus b yy plus c zy. Okay, nice. But now some of this stuff is kind of obviously equal to 0. So notice bracket yy is equal to 0 by bilinearity. Bracket zy is equal to 0 because z is inside of the center. Z is inside of the center because, Well, Z is inside of the derived subalgebra, which is a subset of the center. Furthermore, we wrote that up here. So that's going to collapse to A times Z. A times Z because bracket xy is equal to Z. Okay, but recall that Z is a non-zero vector, so we have a scalar multiple of a non-zero vector is equal to the zero vector. But the only way for that to occur is for that scalar to be equal to 0. So there, we've got A is equal to 0. So now let's play a similar game. So we've got 0 is the same thing as x bracketed with 0. I think that's pretty clear, but then that's the same thing as x bracketed with ax plus by plus cz. But now we'll use linearity of, well, the bracket and write this as a with xx plus b with xy plus c with xz. And then again, some of this stuff is like automatically equal to 0. So xx is equal to 0 because of alternating. Xz is equal to 0 because z is inside of the center, leaving us with b times x times y, or b times bracket xy. But bracket xy is z, so here we have b times z. So again, we've got a similar scenario. We've got the 0 vector is equal to b times z, which is a non-zero vector. So that tells us that in fact, b must be equal to 0. But now let's plug those two facts up here. So plugging those two facts up here, we'll see that that means that c times z is equal to 0, which means that c is equal to 0. So let's step back and see what we've done. We supposed that we had a linear dependence relation for the vectors x, y, and z. And then using all of this calculation, we've shown that the weights here for all of those vectors must be equal to 0. But that's exactly the condition that we need for linear independence. So that means this is a linearly independent set of 3 vectors within a 3-dimensional vector space, meaning that it has to be the basis. Okay, but note that this could be done for any 3-dimensional Lie algebra satisfying these rules. A basis could be chosen so that this happens. So that means that there's a single 3-dimensional Lie algebra up to isomorphism satisfying these conditions. Okay, so let's go over here and write that. So this is going to split into 2 cases. The first, when the dimension, when L prime is contained within the center, and in that case we have L is equal to the span of 3 vectors x, y, and z, where bracket x, y is equal to z. And I guess I should say that all other brackets of basis vectors are 0. But I'll just let that be understood by the fact that none of the rest of them are written here. So that's a classification of 2-dimensional Lie algebra satisfying this rule. Or 3-dimensional Lie algebra satisfying this rule. So before moving on to the next case, I'd like to make a little remark about the last case. And before making that remark, let's notice that we could rename the basis vectors x, y, and z to a-1, a0, and a1. So in other words, L is spanned by those 3 vectors satisfying the commutation or the bracket relations that a1, a-1 is equal to a0, and a0 is in the center. And this is in fact an example of something called a Heisenberg Lie algebra. This is the 3-dimensional Heisenberg Lie algebra. But more generally, a Heisenberg Lie algebra is a Lie algebra with the following basis. So notice it's a minus n, the next one would be a minus n plus 1, all the way up, a minus 2, a minus 1, a0, a1, a2, all the way up to an. In fact, this could be infinite dimensional if you wanted to. And the bracket relations are bracket ak with al is equal to k times delta ak plus l0, a0. And so this is the Kronecker delta. So in other words, that's equal to 1 if k plus l is equal to 0 and 0 otherwise. So notice that this just replicates these bracket relations up here where we only have a1, a-1, and a0. But more generally, we could have this here. Okay, so now that we've maybe made this remark, let's move on to the next case. So next up, we're going to look at the case where the dimension of the derived subalgebra is 1, and the derived subalgebra is not a subset of the center. So that means there's going to be something within the derived subalgebra that is not within the center. But since it's dimension 1, that means that everything in the derived subalgebra is not in the center, I guess, except for the 0 vector, but that's kind of boring. Okay, so now let's take a basis vector for the derived subalgebra. We'll call that x. So we've got L prime is equal to the span of x. And like I said, we know that x is not in the center. That's because if x were in the center, then all of L prime would be contained in the center. And we're supposing that is not true. But since x is not in the center, that means that there exists some y inside of L such that the bracket of x with y is non-zero. Because, well, that's what it means to not be in the center. But then also, we know that the bracket of x with y is inside the derived subalgebra, just by the definition of the derived subalgebra, which is spanned by this single vector x. Then that means that up to scaling, we can choose this y so that the bracket of x with y is simply equal to x. Again, that's after scaling. Really, we know that the bracket of x with y is a non-zero scalar multiple of x, but like I said, we're going to scale y so that this is simply equal to x. Okay, so now let's set L tilde equal to the span of x with y. But notice that this is a subalgebra of L. And we know that this is a subalgebra of L because, well, it closes under the bracket. Bracket of x with x is 0, bracket of y with y is 0, and bracket of x with y is x, which is inside of L tilde. So that means it's a subalgebra. So there we've got a subalgebra. Also, we know that L prime is two-dimensional and non-abelian. But recall that there was a single two-dimensional non-abelian Lie algebra. So that means that L tilde is a copy of this two-dimensional non-abelian Lie algebra. Okay, so now where are we going to go from there? Well, let's extend the basis of x and y of L tilde to x, y, and w, which is a basis of the whole vector space L. So again, we're using linear algebra to do that. And then let's note that if we take the bracket of x with w, well, we're going to get inside of L prime, but that means that the bracket of x with w is simply equal to a times x for some value of a. In this case, that value of a could be equal to 0. Okay, and then we also know that bracket of y with w is also inside of L prime, just by the definition of L prime. L prime, again, is spanned by that single vector x, so that means that the bracket of y with w is equal to b times x. And here, like I said, a and b are inside of the field. So now let's set z equal to alpha x plus beta y plus gamma of z. So we're looking for like a change of basis formula. And hopefully we can make a change of basis formula so that it simplifies nicely. And now let's calculate the bracket of x with z and the bracket of y with z. So I'll skip a couple steps here, but they're easy to check. Notice that both of these should be just multiples of x based off of the fact that, again, x spans the derived subalgebra. So in this case, it's the multiple beta plus alpha gamma of x. And for this one down here, it is gamma times b minus alpha times x. So now looking at those equations, we get some motivation for how we should choose alpha, beta, and gamma. So let's choose gamma to be equal to 1, and then we'll choose beta to be equal to minus a, and we'll choose alpha to be equal to b. But then under that choice, we get the bracket of x with z and the bracket of y with z to be equal to 0. And so again, you can see that just by plugging those values in here. That means that z is in the center of L. So what does that mean? Well, we've got a basis x, y, z. Well, so let's make sure to write that down. So we've got a basis x, y, z of L, where x and y build this two-dimensional non-abelian Lie algebra, and z is, well, it's in the center, so it's a one-dimensional abelian Lie algebra. So in other words, in this case over here, we have L is equal to, well, I'm going to write this as two-dimensional non-abelian direct sum one-dimensional abelian. Of course, like writing abelian for one-dimensional is a little bit like extra, but we'll do it just to underscore this fact. And maybe over here, exactly what's happening in terms of our notation is we have L is equal to L tilde direct sum with ZL, where this L tilde is built out of X and Y, and this ZL is built out of Z. And again, Z was constructed this way down here. Okay, so now we know what happens when the dimension of L prime is 1. Now let's look at the case when the dimension of L prime is 2. Okay, moving on to the case where the derived subalgebra of our three-dimensional non-abelian Lie algebra is two-dimensional itself. And let's recall a special map that we can attach to any vector inside of the Lie algebra called the adjoint map. And, well, let's see, we've got a V inside of the Lie algebra. Add V is a map from L to L. It's actually a linear transformation. And it's defined by add V acting on W is the bracket of V with W. Not only is this a linear transformation, but it is a derivation. Maybe that would be a nice homework exercise to show that it's a derivation. Okay, so starting here, we're gonna make kind of an opening claim. And this opening claim is that in this case where the dimension of L prime is equal to 2, we'll show that L prime itself is abelian. Well, since the dimension of L prime is 2, we can take YZ to be a basis of L prime. So being dimension 2 means we have a basis of 2 vectors. And then we're going to do this thing that we've done kind of a couple times here, and we're going to extend to a basis of the whole space. So XYZ is a basis of the whole Lie algebra L. And then let's point out what our goal is at the moment. So for L prime to be abelian, that would be satisfied if we could show that the bracket of Y with Z was equal to 0. I think that's pretty clear that that would imply that L prime is abelian, given that Y and Z span L prime. Okay, nice. So where are we going to go from here? Well, since Y is inside of L prime, that means that Y is equal to the bracket of Y1 and Y2 for some Y1 and Y2 inside of L. That's simply the definition of being inside of the derived subalgebra. You might say, well, shouldn't I be a span of things like that? But since our dimension is so small and our dimension of our derived subalgebra is so big comparatively, we can actually write it like that. And now let's notice the following. So let's note that if we do the adjoint action of Y applied to W, so that's going to be bracket Y with W, that's the same thing as the bracket of Y1, Y2 with W, given like how we built Y being inside of the derived subalgebra. But now from here, I want to apply the Jacobi identity to this. So that'll allow us to write this as negative, let's see, the bracket of w with y1 itself with y2 minus the bracket of y2 with w with y1. Now we can apply some alternating properties of the bracket to move some things around, and we'll end up with something like this. So this first one is going to be equal to, well, we've got this minus sign out here, and then the bracket of y2 with y1w. And then this next one, the minus sign is going to change into a plus, and we've got the bracket of y1 with the bracket of y2 and w. But now let's note that we could move those things around and then rewrite this as the adjoint action of y1 applied to the adjoint action of y2 applied to w minus the adjoint action of y2 and then the adjoint action of y1 applied to w. In other words, we have the commutator of the adjoint action of y1 and the adjoint action of y2 applied to w. But then since w was really just like a test vector, then that means as maps or as linear transformations, we have the adjoint action of y is equal to the bracket of the adjoint action of y1 and the adjoint action of y2. So let's bring that fact up and see where that takes us. Okay, we just showed that if y was the bracket of y1 and y2, then the map defined as the adjoint action of y was the commutator of the map defined by the adjoint action of y1 with y2. Okay, but now we can apply the trace to both sides and then something kind of special happens. So that means the trace of the adjoint action of y is the same thing as the trace of the commutator of the adjoint action of y1 with the adjoint action of y2. But in a previous video, there was a homework exercise to show that the trace of a matrix A times a matrix B was the same thing as the trace of a matrix B times a matrix A, meaning the trace of a commutator of matrices was 0. But since we could express both of these as matrices, then that means that this is essentially the commutator of two matrices, meaning that we have the trace of the commutator of two matrices, which by that homework exercise was equal to 0. So we have the trace of the adjoint action of y1 is equal to 0. Okay, but what does that mean? Well, that means that if we have the bracket of y with z equal to ay plus bz, then that means the adjoint action of y is represented by the following matrix. So it'll be 0a, 0b. So that's because the bracket of y with itself is 0. That gives us this 0 column right here. But then this result tells us that b must be equal to 0 because the trace is equal to 0. So b plus 0 is equal to 0. Okay, but then applying that here, we see that the bracket of y with z is in fact equal to a times y. Now we just have to show that a is equal to 0. But now we can play the same kind of game. So let's notice that the bracket of z with y, well, that's going to be the same thing as the adjoint action of z applied to y, is going to be the same thing as minus the bracket of y with z, which is minus a times y. But then again, using similar methods to what's up here, we can show that the trace of the adjoint action of z is equal to 0. Again, by exactly similar methods to what we did right here. But then that trace being 0 and then taking a matrix representation of this adjoint action will tell us that a is equal to 0. But then plugging a equals 0 and b equals 0 into our original expression here for yz, we'll see that bracket yz is in fact equal to 0, which is what we wanted to show that L prime was abelian. Okay, so now let's move on from there. Okay, so we just showed that L prime was abelian, and then also let's recall that we're taking y and z to be basis vectors of L prime. But then let's also note that we know that L prime is spanned by the following three vectors. So it's going to be bracket x with y, bracket x with z, and then bracket y with z. Where, remember that x was the vector that we extended the basis of L prime to a basis of the entire vector space L. But we just got done showing that bracket yz was equal to 0. So that means we've got this alternative basis, bracket xy and bracket xz for L prime. So what does that mean? So we've got two bases. Well, obviously there are infinitely many bases, but here we've got two bases for L prime. And those bases are yz and the bracket of xy and the bracket of xz. So maybe I'll call those B1 and B2. But now let's notice that if we look at the adjoint action of x as a linear transformation from L prime to L prime, this is essentially a change of basis map. So this is a change of basis map that takes us from basis B1 to basis B2. You can see that because if you apply adjoint action x on y, you get bracket xy. And if you apply adjoint action x on z, you get bracket xz. And well, we just argued that both of these were bases. So again, that's our change of basis map. But if the adjoint action of x is a change of basis map, just by linear algebra, we know that it's one-to-one and onto. In other words, add x is a vector space isomorphism. Okay, so that's good. So just to have a little bit of a midpoint summary, we've got a basis for L prime, and then we extend that to a basis of the whole space, and regardless of the extension vector, the adjoint action of that extension vector restricted to L prime is an isomorphism. Okay, so moving on to the next step, from here on out, we're gonna assume that we're over the complex numbers because we will use that for our decomposition. So let's recall we've got L prime as abelian, L prime is spanned by y and z. We extended that to a basis x, y, z of the whole space. We showed that any extension there will make add x an isomorphism from L prime to L prime. In other words, it can be represented by an invertible matrix. And then the final structure will be determined by the properties of add x. So our first subcase is, well, we can choose an x in L such that add x is diagonal. Okay, so let's look at that case. Well, that means that we have the bracket of x with y is equal to ay, and the bracket of x with z is equal to bz. And then all other brackets are equal to 0. So again, that's what it means for add x to be diagonal, because if we represent add x in the basis x, y, z, then that means that add x has this form A0, 0b as a map from L prime to L prime. So this represents the y column, the z column, the y row, and the z row, if you will. And now the next thing that we can do is do some scaling here. We can definitely scale one of these so that either a or b is equal to 1. So let's maybe choose the scaling so that a is equal to 1. And then b may not be scalable, like simultaneously. So that means I'm going to change this to a 1 right here. And that's, let's see, by the scaling of x. So now let's say we have another Lie algebra with the same data. We want to decide when those Lie algebras are isomorphic because perhaps we just found an infinite family. So let's introduce some notation for this. So let's call the Lie algebra satisfying these rules right here. So when I say these rules, I mean this and this. We'll call it L sub lowercase b. And then let's take another Lie algebra, L sub uppercase b, to be the span of capital X, capital Y, and capital Z, so that the bracket of capital X with capital Y is equal to capital Y, and the bracket of X with capital Z is equal to capital B times capital Z. So in other words, we've got a similar structure here. Now we just want to decide, well, which values of lowercase b and capital B make this isomorphic. Maybe all values do, or maybe no values do, or maybe there's some sort of rule. So that's what we want to get at. So let's suppose that phi going from L lowercase b to L uppercase b is a Lie algebra isomorphism. Okay. And then let's say that phi takes lowercase x to a1 upper x, a2 uppercase y, a3 uppercase z. And then it takes lowercase y to c1 uppercase x plus c2 uppercase y plus c3 uppercase z. And then finally it takes lowercase z to d1 uppercase x plus d2 uppercase y plus d3 uppercase z. So you might say, well, why didn't I use b's here? And that's because I kind of used up a b in this case right here. Okay, and now I'm going to sketch out the path towards the end. And so maybe I'll leave this as a homework exercise to fill in. So the idea is you want to look at, we have phi of y is equal to the bracket of phi of x with phi of y, because we have a Lie algebra homomorphism or isomorphism, and we can apply the bracket to both sides of this and then use the homomorphism property. And the fact that b times phi of z is the same thing as the bracket of phi of x with phi of z. So that's going to give you a system of equations for these coefficients over here. And those systems of equations should lead you down the path to the following two conditions. Either lowercase b is equal to capital B, that's kind of the obvious isomorphism because we have exactly the same data that is being defining these two Lie algebras, or we have uppercase b is 1 over lowercase b, meaning that we only have an isomorphism between these two types of Lie algebras when the constant lowercase b and uppercase b are equal or they're reciprocals of each other. And you might worry about like dividing by b here, but b is non-zero. We know that b is non-zero because add x is an isomorphism. So if it's in a diagonal form, it has non-zero entries on the diagonal. Okay, so this is a fairly simple calculation that I'll let you fill in as a homework exercise. So what does this mean? Well, this means that in this case where the dimension of L prime is 2 and add x is diagonal, or really diagonalizable, we have this infinite family of Lie algebras that are parametrized by this number right here. Okay, so now let's move on to the next case where add x is not diagonalizable. In other words, we can never choose an x that makes add x diagonal. Okay, so like I just said, the next case, the remaining case in this setup where the dimension of the derived subalgebra is 2, is the case where add x is not diagonalizable. In other words, if we range over all x that extends this basis to a full basis, none of those x's produce a diagonal version of the adjoint action. But that's totally okay because not all linear transformations are diagonalizable. But the ones that aren't diagonalizable have a so-called Jordan canonical form. So that means that we can choose an x so that add x builds its Jordan canonical form. So we've got a repeated eigenvalue. So here we've got add x is of the following form. So it's lambda 1, 0, lambda. So this is a 2 by 2 Jordan block. And this is where add x is going from L prime to L prime again. And we know that lambda is non-zero because that's an isomorphism. So again, this is using the fact that we're over the complex numbers. Of course, there are non-diagonalizable things over the real numbers, the so-called like rotation matrices. So that'll be a homework exercise to look at that. Okay, so what does this mean right here? Well, this means that the bracket of x with y is equal to lambda times y, whereas the bracket of x with z is equal to, let's see, y plus lambda times z. But now we can do some rescaling here, and the rescaling is like pretty simple in this case, to get to the point where that lambda is equal to 1. And so that's going to require a little bit of rescaling of x and y. So I'll let you worry about that on your own. It's not too hard. So like I said, here we can scale x and y so that we get x, y bracket is equal to y, and then x, z bracket is equal to y plus z. But that kind of thing is possible in all of the cases where add x is non-diagonalizable over the complex numbers. So that means in this non-diagonalizable class, there's only a single Lie algebra, and it's the one that we're building like this over here. Okay, so let's move on to the next case where the dimension of the derived subalgebra is 3. Moving on to our last case where the dimension of the derived subalgebra is 3 in a three-dimensional Lie algebra. So again, I'd like to underscore the fact that we're working over C at this point still. I'll point out where we use that. So we're going to start with the following claim, and that says that there exists something that I'll call H inside of L such that the adjoint action of H, seen as a linear transformation from L to L, has a non-zero eigenvalue. So this will be essentially the tool that we use to like finish this whole thing off. So how does this go? Well, we're going to take any non-zero vector, I'll call it x, inside of L. And then this is going to break into two cases. In one case, we're pretty much done. So if add x has a non-zero eigenvalue, then we're done, and we can simply set h equal to x. And so let's suppose that's not the case. So otherwise, well, what does that mean? That means that all eigenvalues of add x are equal to 0. Now we're going to do something that we've done several times here, and let's extend x to a basis of the whole space. So we've got x, y, z, a basis of L. Okay, great. And then let's notice that L is the same thing as L prime. Well, that's sort of by our setup up here. We know that the dimension of L prime is 3. L prime is a subspace of a three-dimensional vector space, so it's got to be the whole thing. But then also, L prime is equal to the span of x with y, x with z, and then y with z, just by the definition of having a basis right here. But that means that we've got 3 non-zero vectors. That's the only way to have a three-dimensional vector space right here. So that means in particular, this is non-zero and this is non-zero. But then that means that the Jordan canonical form of add x is equal to, well, the following matrix. So 0, 1, 0, 0, 0, 1, and 0, 0, 0. So having zeros on the diagonal means that all of the eigenvalues are 0, but then the fact that add x produced 2 linearly independent non-zero vectors means that we've got a Jordan block of this form. So recall that there are 3 3x3 Jordan blocks. There's one with everything on the diagonal, there's one with 1s on the off diagonal here, and there's ones with a 1 on the upper right entry. But the upper right entry would indicate that only one of these was non-zero, which is not the case right here. So what does this mean? So that means that we can make a choice of x, y, and z such that the bracket of x with y is equal to x and the bracket of x with z is equal to y. Well, that's what this Jordan canonical form means. It means that we can choose a basis so that this matrix is indicating what's happening in that new basis. So that's what we've done here. We just haven't renamed things. So we've essentially forgotten our previous x, y, z, and we've renamed them here. Okay, but now let's look at this first formula, this bracket xy equals x, and note that we can rewrite this as bracket yx equals negative x. Oh, but then we can write that as add y on x equals negative x. But there, that means that add y has an eigenvalue of -1 corresponding to the eigenvector of x. So now what we'll do is we'll set y equal to h, because that h is the vector that has a non-zero eigenvalue. Okay, so now let's take that. Okay, we've got this vector h inside of L that has a non-zero eigenvalue. And so now we want to call the corresponding eigenvector e. So let's do that. So let's call the corresponding eigenvector e. So what does that mean? That means that the bracket of h with e is equal to some number, I'll maybe call it a times e, where a is non-zero. But now what we'd like to do is do some scaling that turns a into the number 2. So let's do that. So we'll put here that we're going to scale so that h with e is equal to 2 times e. Actually, before we move on, I'd like to point out that in the last step where we did the Jordan canonical form, we used the fact that we were over the complex numbers. You know, otherwise we wouldn't necessarily have a Jordan canonical form like that because we could have been wrapped up into complex conjugate eigenvalues. Okay, so now that being said, we have scaled h so that the bracket of h with e is equal to 2e. So now let's also note the following, that the bracket of h with h is equal to 0, which is 0 times h. So what does that mean? So that means we have the following two eigenvalues of h, 0 and 2. Okay, but then let's also notice that h is an element of the derived subalgebra. That's because the derived subalgebra is everything. Okay, but that means that the trace of the adjoint action of h is equal to 0. So we used that earlier in the video. But then the trace is also equal to the sum of the eigenvalues. So that's a fact from linear algebra. So what does that mean? Well, so far the sum of the eigenvalues is 2, but we know that the sum of the eigenvalues should be 0. But that means we need a new eigenvalue, and that new eigenvalue will be -2, so that we get a sum of 0. And then let's call the vector associated with this eigenvalue f. So at the moment, what do we have? Well, we have h with f is equal to -2f, and then h with e is equal to 2e. So that's almost everything we need for L to be isomorphic to SL2. You know, the nice three-dimensional Lie algebra that we work with all the time. So there's one last thing to finish that off, and that is to find the bracket of e with f. And so let's do that with the following calculation. So let's do the bracket of h with the bracket of e with f. And we'll apply the Jacobi identity. So this will be negative the bracket of f with the bracket of h with e, and then minus the bracket of e with the bracket of f with h. Then this is going to be equal to negative the bracket of f with 2e, given the fact that h with e is equal to 2e. And then finally minus the bracket of e with 2f. That's because this is like reverse. We know h with f is minus 2f, but that means f with h is 2f. But now notice by bilinearity and the alternating property, this is going to turn into 0. So what does that tell us? Well, we've got the bracket of h with ef is equal to 0, but that means that the bracket of ef must be a multiple of h. So that means we have bracket of ef is equal to some multiple of h. But we might as well scale it so that it's just the multiple of h given by 1 times h, in other words, h. So let's see what we have. Well, we've got 3 vectors inside of L. Those vectors are h, e right here, and f right here. They span L. And then the bracket relations between these vectors are h bracketed with e is 2e, h bracketed with f is minus 2f, and e bracketed with f is h. So that means that our Lie algebra, our 3-dimensional Lie algebra over C, where the derived subalgebra is also 3-dimensional, must be SL2, because these are the bracket relations for SL2. So that fills in the remaining part of this thing right here. We have SL2C. Okay, so now I'm going to leave you with some exercise. I've got 3 nice exercises that build off of what we did today. So the first is to fill in the details to show that L sub B is isomorphic to L sub capital B if and only if B and B are the same or they're reciprocals of each other. So where this showed up in the case where we're looking, down here at 3-dimensional Lie algebras where the derived subalgebra was dimension 2. Okay, so the next is to show that over R, the real numbers, there are exactly 2 non-isomorphic Lie algebras where L prime is equal to L. And I guess I should say here of dimension 3. And those two are SL2R and R3 with the cross product. So over the complex numbers, these are the same as we showed down here. But over the real numbers, they're not. And then as like a little open-ended project, you could explore what's happening over ZP, or a more general field of characteristic P. And then let's have our third exercise also be related to the case where we may be restricted to the complex numbers. And let's explore 3-dimensional real Lie algebras where the dimension of the derived subalgebra L prime is 2, and then add x has 2 complex conjugate eigenvalues. So if there are 2 complex conjugate eigenvalues, then it's diagonalizable over the complex numbers, leading to this case right here, but it's not diagonalizable over the real numbers. So you've got to look at it using slightly different techniques, and that's a good place to stop.